Hi, this is lesson 2 for unit 4, and in this lesson we're going to go ahead and talk about Graham's law of diffusion, plus we're going to go ahead and talk about Dalton's law, plus what is STP. For our lesson objective, students will learn how to calculate the rate of diffusion of a gas and how to solve for the total pressure of a mixture of gases.
Let's start with Graham's law. First part of Graham's law is understanding what is diffusion. Diffusion is the random scattering of one material through another. In the picture you see right there, we have a drop of food coloring being placed in a cup of water. And that food coloring will go ahead and diffuse throughout the whole cup. Eventually, it will be evenly spread out. Now, that's an example of a liquid diffusing through another liquid. Now, diffusion could happen between liquids and gases and other gases, and even liquids and solids and so on. So that is diffusion. Very similar to it, it's effusion. Effusion is the movement of gas molecules through a pin-sized opening. So in the pictures here right there, there's a tiny opening dividing both chambers, and the gas molecules are moving through that small opening. That is effusion. Graham's law can be used to measure the ratio of effusion of two separate gases. So that's an application of Graham's law. Further application of Graham's law includes a separation of gases with different densities and the finding of molar masses of unknown gases. Now we're going to go ahead and use a PhET simulation to study diffusion of a gas. In this PhET simulation, we're going to go ahead and see two types of molecules. We have some 20 molecules in teal color and 20 molecules in red color. The number of particles is 20 for each, and their masses are different. In teal, the mass is 32 AMU, as you see on the top right corner of the screen, and the red molecules are only 4 AMU. Now, as we start the simulation, you're going to go ahead and see that the teal molecules were heavier at 32 AMUs. They move a lot slower. On the other hand, the lighter molecules, which has 4 AMU in red, they're moving a lot faster. Difference in speed is what allows us to go ahead and separate the molecules during effusion. Now, what we're going to go ahead and do here is remove the divider in between them and let it go for a couple of seconds, and then keep track at the very top of the movement of molecules from one side to the other. So let's go ahead and do that. Remove the divider, let it go for a couple of seconds, and I stopped it. Now you can see after about 2 seconds, there are 7 molecules on the left-hand side that are red, so they transfer from the right side over to the left, and about half as many blue on the right-hand side. Why were there so many more molecules on the left side? Because they're moving faster, because they're much lighter. So this is a process that could be used to separate molecules due to their different velocity, because of the difference in either density or because of the difference in mass. Next, let's go ahead and take a look at the formula for Graham's law. In the formula for Graham's law, right there at the bottom, you see that we have rate and mass, and they're equal to each other. Now, the formula states that the rate of diffusion of a gas is inversely proportional to the square root of its molar mass. What that means is that the heavier the molecule, the slower it's going to go. So that's an inversely proportional relationship, and vice versa. The lighter the molecule, the faster the molecule will travel. Because it's an inversely proportional relationship, that's why you see the rate of A on the numerator and the mass of A on the denominator, because they are inversely proportional to each other. On the other hand, B here is in the denominator. You'll see the mass of B on the numerator, again, because they are inversely proportional to each other. So that's why they're crisscross. So you have to get the square root of the mass of each other, simplify, and that will give you a rate for how much faster A might be when compared to B.
In example 2, we're asked the following question. Find the rate of effusion of the following gases. And we're going to go ahead and compare in part A, methane gas, which has a formula of CH4, versus pentane gas, which has a formula of C5H12. So our very first order of business is to figure out the molar mass of both methane and pentane. Once we have the molar mass, we're going to go ahead and substitute them into this formula here for the mass, get the square root of their mass, and then we're going to go ahead and simplify it by dividing by the smallest of the two. But first things first, let's get the molar mass of each of those. So for methane, CH4, we're going to count there is 1 carbon atom and 4 hydrogens. Next, we use the periodic table to find the molar mass of carbon, which is 12 grams per mole. And the molar mass of hydrogen is 1 mass per mole. So that's going to go ahead and multiply. That's going to give us 4 for a grand total of 16 grams per mole. The molar mass of pentane there's 5 carbon atoms. Each one has a molar mass of 12. So it's going to give us 60. And there's a total of 12 hydrogens. Each one has a molar mass of 1. So total of 12. Add them up. We're going to go ahead and get 72 grams per mole. That's the molar mass of pentane. Now we're going to go ahead and let's see. The rate of A, we're going to call that methane. Notice that the mass you put in on the denominator, even though the rate of A, which in this case methane, is in the numerator, because mass is inversely proportional to the speed at which they effuse. So the heavier the gas, the slower it's going to go ahead and effuse. So I'm going to go ahead and put rate of, rather than call it A, we're going to call it what it is, CH4 methane. And I'm going to put its molar mass of methane is 16. And on the denominator, I'm going to put rate of pentane, C5H12, molar mass of it is 72. And for each one of these, I get their square root. Square root of 16 will give me a 4. And square root of 72 is 8.48. Next, I want to go ahead and simplify. So I'm going to divide by the smallest number. In this case, that's a 4. So I'm going to divide both sides by 4. So I get a 1 here, and 8.48 divided by 4, it is 2.12. Alright, so that's my answer. So I could make the claim that methane is 2.12 times faster than pentane when they effuse. So that's part A of example 2. Let's go ahead and take a look at our next part, which is part B. In this part, they ask you guys, find the relative rate of diffusion for hydrogen gas versus nitrogen gas, H2 and N2. Alright, so let's go ahead and solve for that. Again, we're going to begin by getting the molar mass of each one of those two gases. So for hydrogen, molar mass of hydrogen, there's only 2 atoms of hydrogen. Each one has a molar mass of 1, so it's a total of 2.0 grams per mole. And for nitrogen, very similar, N2, there's 2 atoms of nitrogen, molar mass is 14, so it's going to give us 28 grams per mole. Now I know that hydrogen is lighter, so it's going to go faster, but again, the question is not who's faster. We know it's hydrogen because it is the lighter of the two, but how much faster is hydrogen when compared to nitrogen? So now we're going to go ahead and plug them in here. So I'm going to put the rate of hydrogen gas, it's equal, I'm going to put the mass of hydrogen gas, which is 2. On the denominator, I put rate of nitrogen gas, molar mass is 18. So I crisscross them again because they're inversely proportional. Get the square root of each one of these, 1.41 for square root of 2, and square root of 28 gives me 5.23, 5.29. Now I'm going to go ahead and divide by the smallest of the two just to simplify. So that will give me a 1 here, and make the equal a little bit bigger, divided by 0.41. 3.75. So hydrogen is 3.75 times faster when compared to nitrogen gas. Alright, let's go ahead and move on now to part C of example 2. In this one, they ask you a very similar question. Find the relative rate of effusion of helium gas versus propane gas. Now helium gas is just helium. There's only 1 atom of it, so that's going to simplify our lives a little bit. Helium has a molar mass of 4.0 grams per mole. Now for propane, there's 3 carbons and 8 hydrogens. Molar mass of carbon from the periodic table is 12.0, so it's going to give us a 36. For hydrogen is 1.0, so it's going to give us an 8. 44.0 grams per mole. So those are the molar mass for helium and for propane. Now again, we put them into the formula, so I'm going to say the rate of helium is, molar mass of helium is 4, again I crisscross them. The rate of propane, C3H8, molar mass is 44, I square root each one of these. Square root of 4 is 2, square root of 44 gives me 6.63. And now I'm going to go ahead and divide both sides by 2 just to simplify it a bit. And we get, rounded off slightly, 3.32 over 1. So that means that helium is 3 times, a little bit more than 3 times faster, 3.32 times faster than is propane. Alright, so that takes care of example number 2. Now our next problem is going to be a critical thinking problem. In this one, we're asked to go essentially backwards and figure out the mass of a gas. So they ask you, 2 gases are allowed to diffuse. The first gas has a mass of 16 grams per mole and is 5 times faster than the second gas. What is the mass of the second gas? Alright, so the first gas is faster. So that means that the second gas has got to be heavier because it's slower. So let's go ahead and plug in the numbers. Alright, so we're going to call it gas 1 and gas 2, or gas A and B. Alright, so we put the rate of gas A, which we know its molar mass is 16, so I'm going to put in the denominator, 16. Alright, and then the rate of gas B, which we don't know what it is, its mass. We don't know what it is. Alright, but we do know this. A is 5 times faster. That was given to us. It is 5 times faster than the second gas. Alright, so after we square root them, we still don't know what this is, so I'm going to leave it blank, but this is going to be a square root of 16, that's a 4, and after we divide, that's a 5 right there, 5 over 1. How do we get that? Because we know that it was 5 times faster. A is 5 times faster than gas B. Alright, so what we're going to do is now go backwards, figure out this number, and then figure out that number, so we can get the molar mass of the missing gas. Alright, so what number divided by 4 will give me 5? The answer for that is 20. 20 divided by 4 will give me 5. So you see how these two expressions are the same. Now, square root of what number will give me 20? Alright, so to go backwards, we're just going to go ahead and square it. The answer for that is 400. 400, square root of 400 will give me a 20, and the 20 divided by 4 will give me a 5. So that is our answer. B, the molar mass of B, is 400 grams per mole. And that's our answer for our critical thinking problem.
Next is Dalton's Law. Dalton's Law states that the total pressure of a mixture of gases is equal to the sum of the partial pressure of the gases in the mixture. So if you add up each of the individual gases, they will add up to the total of all the pressure of the gases put together. Now, Dalton's Law is applied when perhaps filling the tank of a scuba diver, also when you collect a gas over water. Here we have potassium chlorate and is being heated. Now that's going to break down into potassium chloride and oxygen, and that oxygen is going to go ahead and bubble through water. So this is collecting it over water. Now the gas that is on the top of this bottle is going to contain both the pressure from the oxygen that was created during the decomposition of potassium chlorate, plus some water vapor is going to pick up along the way. So we can use Dalton's Law to go ahead and figure out the actual pressure of the oxygen that was collected from the decomposition of potassium chlorate. Here's the formula for Dalton's Law. To get the total pressure, you need to just add up the partial pressure of each of the gases held in the container. For the picture right here, you have this first glass, the partial pressure of first glass, which is just 1. And then the partial pressure of the second gas, which is 2. And if you were to put them into a container of the same size and at the same temperature, to get the total pressure, you just add up the pressure of the first gas plus the pressure of the second gas. In the formula you see it says P1 plus P2 plus P3 plus Pn. That just signifies that you can have many, many gases. So all you have to do is just add them together. Now let's go ahead and take a look at some problems for Dalton's Law.
In example 3, we're asked the following question. The tank of a deep sea scuba diver contains 1,320 atm of nitrogen gas, 630 atm of oxygen gas, and 1,050 atm of helium gas. Find the total pressure of the mixture. Alright, so we have 3 different gases all put together into this scuba tank. So the partial pressure of first gas, so I'm going to put P for first gas, which is nitrogen gas. So I'm going to put N2 for nitrogen gas. The partial pressure of that gas is 1,320 atms. The partial pressure of our second gas, in this case, it's oxygen gas. So I'm going to put PO2. That's a total of 630 atm as well. And the partial pressure of our third gas, which is helium, is 1050 atm. And the question is, can you find the total? In Dalton's law, to get the total, all you do is add the partial pressure for each of the gases, and that's what we're going to go ahead and do. So I'm going to put P total, and that will give us our answer. My calculator, let's plug it in. 1320 plus 630 plus 1050 gives us 3000 atm, and that is the total pressure for the scuba tank. That takes care of example 3. In example 4, we're given the following problem. It says, an evacuated container is filled with 2.5 atm of oxygen gas and 200 psi of nitrogen gas. And then we're asked, what is the total pressure of the container in torr? A couple of things about this problem. It began with an evacuated container. What does that mean? It means that the container is empty. There's nothing in it. Alright, now they give us two pressures, and you will notice that to increase the difficulty, they gave it to us in the wrong unit, atm and psi. So they're mismatched units, and also the final answer is requested in torr. So what we're going to go ahead and do is change those atm and psi from those units to torr, and then we can go ahead and do Dalton's law where we just add them together to get the total pressure. So let's go ahead and get started. For the atm, we're going to put 1 atm on the denominator, so the given and the denominator match, so they can cancel each other out. And then the numerator, 760 torr. Get that in a second. For the psi, it's going to go ahead and be 14.7 psi. Again, notice the units match, so that they can cancel out. And on the numerator, we're looking for torr, so I put torr in the numerator. From there, we just go ahead and get our calculator, and now we can go ahead and change them to torr. So it's going to go ahead and be the first one, 1900 torr. And for the second one, I got 200 psi times 760 divided by 14.7. That's going to go ahead and give me, I'm going to round it up slightly to 10,340 torr. So now we got the partial pressure of each of the gases. Now you want the total pressure. You add up the partial pressure for each one of these. So I'm going to go ahead and do that. The partial pressure of oxygen, which is 1900 torr, plus the partial pressure of nitrogen gas, which was 10,340 torr. Add them up to get the total pressure. So I'm going to put P total. So that's going to go ahead and give us 12,240 torr. So that is our answer for example number 4. In example 5, we're giving the following question. An empty container is filled with 630 psi of hydrogen gas, 25 atm of helium gas, and 1000 kPa of neon gas. Find the total pressure in the container. Alright, so a couple of things about it. Can we just add them up together like we do in Dalton's law to get the total pressure? Sure, but first we need to have matching units. And right now they're not. We have psi, atm, and kPa. Now, they did not tell us which unit they wanted, so let's go ahead and just choose one. Since the first one's already in psi, let's switch the other two to psi, and then we'll just add them together to get our final answer, which will be in psi. So I'm going to go ahead and change atm to psi, so the math for it will look like this. I'll put in the denominator 1 atm, because the given in the denominator always match so they can cancel each other out. And I'll put 14.7 psi on the numerator, because I want my answers, all of them, to be in psi. And for the kPa, I'm going to put 101.3 kPa. That's going to be in the denominator. And on the top is going to be 14.7 psi. Okay, so now we're going to have all three answers as psi, so they have the same unit. Then we can go ahead and add them together to get the total pressure for the gas. So for the first one, it would be 25 times 14.7 divided by 1. So it's going to go ahead and give us 367.5 psi. Next one, we have 1000 times 14.7 divided by 101.3 kPa. That's going to go ahead and round it off slightly to 145.1 psi. So now that we all have the same unit, now I can go ahead and add them together to get the final answer. Alright, so let's go ahead and do that. We have 630 psi for our first gas. Alright, let me go ahead and add a .0 at the end so that the decimals can line up nicely. For the next one we have 667.5 psi, this will be our second gas. And for our third gas, 145.1 psi. Now we're going to go ahead and add them all together to get the total pressure. So P total, it's all of these added together. The answer will be in psi, so it's going to be 630 plus 367.5 plus 145.1. It's going to give us a total of 1,142.6 psi, and that is our answer for example number 5. In example 6, we're asked the following question. An evacuated container has a total pressure of 100 atm. If the container is filled with 810.4 kPa of hydrogen gas and 11,400 millimeters of mercury of oxygen gas, then what is the pressure of the third gas? Alright, so that is the problem. So I'm going to go ahead and write it out a little bit, put all the information up on the board. First of all, there's 3 gases, and notice in this problem they're asking us to figure out the partial pressure of one of the gases, so that's missing. We do have the total. Alright, so gas number 1 was hydrogen gas. So I'm going to put the pressure of hydrogen gas, and that was given to us was 810.4 kPa. Then gas number 2 was oxygen gas. So I'm going to put partial pressure of oxygen gas was 11,400 millimeters of mercury. Gas number 3, that we do not know. So I'm going to put an X in its place. But at the very beginning of the problem, they told us the final answer, which is the total, if you add them all together, is 100 atm. So that is the total pressure. After we add them all up, it's going to be pressure total. It's 100 atm. And now here comes the final part. Find the pressure of the third gas. By the way, they want the answer in psi. So our first step is going to be, well, we need matching units. So we're going to change all of those given units to psi. So that's going to be our first step. So the kPa needs to be in psi. So I'm going to put 14.7 psi on the top. On the bottom is kPa, because they got to match so they can cancel each other out. That'll be 101.3. Here I'm going to put psi on the top, since that's what we're looking for. And then the denominator, millimeters of mercury. So that's going to be 760 mmHg. And here it's in ATM. I'm going to put 14.7 psi. And that the denominator is ATM. And it's just 1 ATM. So now we get our calculator, get the value for each one of those. And we're going to end up with 810.4 times 14.7 divided by 101.3 will give us 117.6 psi. That's for our first gas. For our second gas, we have 11,400 multiplied times 14.7 divided by 760. It's going to give us 2,200.5 psi. Third gas we don't know, that's actually what we're solving for. And if we add them all together, well, let's get the final answer. So we have 100 times 14.7 divided by 1 will give us 1,470 psi. So now this becomes a math problem. You have this plus that plus some number x will give us 1,470 psi. So solving it, let me go ahead and do the math here. So I know that the first gas, 117.6, plus the second gas, 220.5, plus x, that's our third gas, equals 1470. So what is the value of x? In your math class, what would you do first? Probably add both of these together. So let's do that. 117.6 plus 220.5, that gives us 338.1 plus x equals 1,470. Now, what are we going to do? Well, we're going to isolate the x. We're going to subtract both sides by 338.1. So after I subtract that from the left side, from the right side, 1470 minus 338.1 will give us a final answer of 1,131.9 psi. And that is the final answer for this problem. And that takes care of example number 6.
Finally, we're going to go ahead and wrap up our lesson while talking about STP. STP is an acronym for standard temperature and pressure. The values for standard temperature and pressure is 0 degrees Celsius, 273 Kelvin, or 32 degrees Fahrenheit for standard temperature. All of those are the same temperature in just different units. For standard pressure, that is 1 atm, 760 millimeters of mercury, or 14.7 psi. Again, all of those are the same pressure in different units. Now, why is it important to have a standard value for temperature and pressure? Well, the volume of a gas may vary depending on the temperature or pressure of a lab. For example, a lab in Denver could give you a different result as a lab in India if they have a different temperature and a different pressure. Even if they do all the steps the same, they're going to go ahead and give you different results for a gas that is collected. So ideally, when scientists release their results, they do a little bit of adjustments for the pressure of the room and the temperature of the room. So that way, it makes it easier for scientists to compare the results from anywhere around the world without worrying about the temperature or pressure of the particular lab where the experiment took place. All right, this brings us to the end of our lesson, and thank you so much for watching.